So up until this point, all of our forces were either straight up or straight down or straight left or straight right, and we didn't have to deal with anything at an angle. But obviously in the real world, there are forces that aren't just straight up and down and left and right. So we have to learn how to deal with forces at angles, and since forces are vector quantities, just like velocity was, we essentially just have to break it up into vertical and horizontal components, just like we did with our initial velocities for our projectiles. So let's look at a few examples. Here I have that wrecking ball again. So if I have a ball of mass 80 kilograms that is stationary, and it's got two cables, one going this way and one going that way, and I want to find the tension in those cables. First thing I would do is to draw a free body diagram. So I've got a gravitational force acting down on this ball. I've got a tension this way, I'll call it T1, and I've got a tension this way that I'll call T2, and it is at a 50-degree angle, just like the other diagram here, right? So I can break this force at an angle up into Ft2 in the x direction. How's that for a whole lot of subscripts? And Ft2 in the y direction. So these are the vertical and horizontal components. And when you think about these forces here, these are replacing this force. A force right and up would give you the exact same results as this force up and to the right here. So it's not that I have these in addition, it's that I can replace this guy with these two guys. Alright, so first let's look at things in the x direction, and what you want to do is you want to ask yourself if the forces are balanced or unbalanced. If an object is stationary, the forces are always balanced, but it can also be moving as long as it's moving with a constant velocity. But in this case it's stationary, so we know that in the x direction we have balanced forces. Whenever we have balanced forces horizontally, we know that all the forces are going to cancel out. This means we have a net force of 0. And if you wanted, you could say, you could write all of your forces and have things going one direction positive and things going the other direction is negative, and add them all up and they will add up to 0. But I think it's a little easier just to say, well, if they're balanced, then all the forces to the left have to equal all the forces pulling to the right. And if we set it up this way, we don't have to worry about positive and negative signs. We're just going to have positive signs. I mean, essentially you could subtract this over and make it negative and it would equal 0 like I mentioned earlier, but let's go with this. So to the left I only have one force. I've got Ft1. And to the right I have not Ft2, but I've got this component, the x component of T2. Now I don't know either of these numbers, so I can't get anywhere yet, but I'm kind of building my arsenal of equations that will allow me to solve for things later on. Okay, now in the y direction, just like with projectile motion, we had to analyze each direction separately. So you can have balanced forces in one direction and unbalanced forces in the other direction. But in this case, with a stationary object in the y direction, they are also balanced. So I can go ahead and, similar to saying left equals right, I can also say that all the up forces will add up to equal all of the down forces. Okay? In this case, our up force is the y component of tension 2, and the down force is gravity. Now with this equation here, I know gravity because I know the mass. Gravity is mass times little g, which on Earth is 9.8. So force of gravity is 80 times 9.8, which is 784. So I know that Ft2y is also 784 newtons. Now what were we trying to find? I didn't write it down, but I asked you to find the tension in the two cables. So that is what we're trying to figure out, right? Well, I found this side of my triangle over here, so I can go ahead and put it over here. And if I know this leg of my triangle, and if I know my angle, I can go ahead and solve for the hypotenuse of this triangle, or FT2, right? So in order to do that, I can have, since this is the opposite, I'm going to have sine of 50 equals opposite over hypotenuse. So my opposite is my 784 over hypotenuse, which is FT2. If I rearrange this, I'm going to get FT2 equals 784 over sine of 50. Throw that puppy in your calculator and you get 1023 newtons. Okay, so there is FT2. We got one of them solved. Check. Okay, now I need to find FT1. Well, I need to find the other component. Let me maybe draw some lines here so we don't get too confused with what we're doing. Alright, so if I can find this other side of my triangle, then I know FT1. Right now I know the hypotenuse and the opposite, so you could use Pythagorean theorem if you'd like. I'm going to use tangent because I want to use the original number that I was given. So I know that tangent of my angle, so tangent of 50, is going to be opposite over adjacent, so 784 over FT2x. Again, I rearrange and I get FT2x equals 784 over tangent of 50. And if I plug that guy into my calculator, I get approximately 658 newtons. That's an ugly 8, but anyway. Okay, so there we go. Found both of them. This is kind of the important part here that I want you to take from this example. Separate out the forces in the horizontal direction and the forces in the vertical direction. This equation is always going to be true when you have balanced forces, which is when you're not moving or moving at a constant velocity. Then you have to figure out what specific forces go in. Sometimes it could be more than one. You can have more than one force up or down or whatever. Okay, moving on to another example, we're going to look at a little bit more complicated situation here. We have a guy pushing one of those old-fashioned push mowers. I guess they're not so old-fashioned anymore. People are using these more lately. He's exerting a force down on it to get it to go forward. We are going to assume that there is some friction as well. And we are going to say that the mass of this mower thingy here is 30 kilograms. Alright, and actually we'll say that you know the push force. Say that that's given. This guy is exerting 100 newtons of force down and to the right on this mower, and we are going to try to figure out the normal force acting on the mower and how much friction is acting on the mower if this thing is moving at a constant velocity. Alright, so pushing mower, constant velocity, this is what we're given, this is what we're trying to find. First thing I would do is start out with a free body diagram. So we have gravity pulling down on the mower, and we could figure that out. It's going to be 30 times 9.8. Okay, so that works out to be 294 newtons of gravity. Okay, I have a normal force up. Even though the force is at an angle, the ground is still level, so we have a normal force going up. We don't know what that is. We've got friction to the left because it's in the opposite direction of motion. And this push force we tend to not draw, even though this diagram shows an arrow going in. We like our arrows coming out, so I'm going to kind of extend that arrow out this way and say that this is my 100 Newton push force over here, and that is at a 45-degree angle with respect to the horizontal. Okay, so here we go. If we look in the x direction, we are moving now, but I mentioned that we're at a constant speed. So yes, we still have balanced forces. So that means that we can have the forces to the left equal the forces to the right. If that were not true, we would not be balanced. force to the left is friction. That's the only one going that way. To the right, I have not all of the push force, but this component of the push force, what I'll call Fpx. Okay, at this point I can find Fpx because I know Fp, so I can now find friction without analyzing the vertical forces at all. Fpx is going to be 100 times, you could use sine or cosine since it's 45, but let's be accurate and we'll use cosine of 45. Okay, plug that guy in your calculator, make sure your calculator is in degrees, and you get 70.7 if you round newtons. So there is my Fpx, which is also equal to friction. Okay, so we found one of the two things we're looking for. Now if we look in the y direction, because the x direction isn't going to tell me anything about the normal force, again we are balanced because this thing is not accelerating up or down. So our equation is going to be up equals down. The only up force is the normal force, so that's easy. And now sometimes it's easy to forget this push force has a vertical component. So in addition to gravity, we also have Fpy pushing down. So I'm going to say gravity plus Fpy. So just looking at this, the normal force is going to be greater than if we weren't pushing on it at all. Because we're pushing down, that makes the normal force go up a bit. Alright, so if I kind of bring that equation over here, I'm going to have the normal force, which is what I'm trying to solve for, is equal to gravity, which I know, 294, plus Fpy. Well, I know that these two legs are going to be equal because it's a 45-degree angle. So I know when I found Fpx, I also found Fpy. So 70.7 goes there as well. And I add those two guys together, and I get 364.7, or you can round it to 365 newtons of force. So quite a bit going on. You need to I would be careful to kind of have a bookkeeping system or some way of keeping track of all this information. Don't just jump in and hope that everything goes where it's supposed to go. So we were able to find friction and the normal force while the mower was moving at a constant velocity. Now let's look at this situation again. But now let's say instead of being at a constant velocity, we're going to have an acceleration to the right of 2 meters per second squared. Okay, so exact same situation. Sorry, the picture's not here anymore, but you can go back if you want. Mass is still 30 kilograms, and now I want to know what is the, let's assume that friction remains constant, so that didn't change. And I want to know what is the push force required to get this object to accelerate. We're going to have to push with something greater than 100, right? Because when we pushed with 100, there was no acceleration, so we're going to have to push harder, and we can look at the push required. So our free body diagram is essentially the same, only now I guess our push force should be a little bit longer, but all the angles, everything is going to be identical. Gravity is still going to be 294. Just because you push on it doesn't change gravity. The normal force is not going to be the same because you're pushing down harder. Friction doesn't change with speed, so the fact that we're accelerating shouldn't change that. So we're good having that being 70.7 newtons. And our push force here is what we're looking to find. So let me jump over here, and we're going to say in the x direction. Actually, let's start with the y direction. Grab my eraser here. Oh, didn't work. Try that again. There we go. Okay, so let's look at the y direction first. The y direction, we're not accelerating up or down, so again we have balanced forces. So we've got the normal force up, because we can still say that the up forces equal to down forces. We've got gravity down plus Fpy, vertical component of our push. I don't know the normal force, so I can't solve for Fpy using just the vertical stuff. Let's jump up here to have a little more room for the x direction. Now this time I'm accelerating to the right, so now we have unbalanced forces in the x direction. And so this is our first time seeing how to deal with that. If they're unbalanced, we can't say that left equals right, but we can say that the net force is equal to mass times acceleration. And the net force is going to be the force to the right minus the force to the left in this case. Again, you could always just have positives one way and negative the other way, but if you want to always have accelerations positive, you can just take the bigger force minus the smaller force, and then your acceleration will be positive, and you'll just have to remember which way it's going. So in this case, the bigger force is going to be Fpx minus the smaller force of friction equals ma. Now in this equation, we have everything except Fpx, so we can solve for Fpx. We've got friction, that's 70.7. We've got mass is 30, and our acceleration was given as 2. So we crunch a few numbers, and we end up with Fpx equal to 130.7 newtons. Okay? Now we don't want Fpx, we want Fp, right? So if I know this side of my triangle is 130.7 newtons, and if I know that this is a 45-degree angle, I can say that the cosine of 45 equals adjacent, so 130.7, over hypotenuse, which is the entire push force, which is what we're trying to find. So push force equals 130.7 over cosine 45. Okay, and we end up with a push force of 185 newtons. So we had to push almost twice as hard to get this guy to accelerate. We could then go find our normal force, but it wasn't asked for. So there you have it. These are the types of problems you'll be dealing with. Have fun.